Okay, so this is actually that problem right here. Okay, and what you're going to notice is it's very, very similar to just a normal sort of SN2 reaction, right? The only difference being that when we do this substitution and attack, we're going to actually have the leaving group not actually leave the entire molecule. Okay? Okay, so again, our attacker is going to be this one right here. We'll have this right here as the negative oxygen, right? That oxide. And this is going to attack the position that has less blocking, right? And so we'll attack right there. Okay. That's our mechanism. And then our leaving group kind of leaves. Yeah, we leave that carbon, right? Yeah. Kind of. All right. And so this is going to break that bond, put the negative charge here, and that will leave us this one here. Remember, for the geometry, we need to do the backside attack. And so this is on this side, so it has to attack from that side, right? And we'll get our product here on this side here. Now, note this is going to cause this to go from bottom going away from you, right? It'll flip up going away from you now, because we backside attacked it, right? Okay. So instead of being downwards like this, we're coming up in this direction. And so it's going to flip it to the top position. Okay. And that's what's going to dictate our geometry right there. Because again, it's backside. This is in the plane, right? So backside attack means this one has to be in the plane, but down rather than up. Okay. All right. This second step is actually really important. If you kept this like this, you would have this powerful base slash reasonably good nucleophile, and you could do other reactions. So you have to add an acid to neutralize that to get the final alcohol. Okay, and that's oftentimes called an acid workup, where you kind of neutralize all your bases, all your other products, any remaining reactant would get neutralized, and you'll just finish the reaction. A little bit acid. You don't need anything super concentrated, just something fairly mild actually will work. Okay. Anybody have any questions there?
I'm confused. Why is it not like a way for the
because you're not attacking these directions. You're not doing it into the plane or out of the plane. So when we're doing the backside attack here, we can accomplish the exact same thing by attacking from the bottom. Normally we end up attacking kind of from the actual like out of the plane, right? Because everything else is straight. Basically, we normally look like this, and then we're attacking from like here. In this case, we're like this, and so we're attacking from here. So anything that's away or towards you stays away or towards you. It's just going to flip up or down. Kind of like if we have the umbrella and we're pushing it upright. If we push it up this way, the same ting that's in this direction is going to stay in that direction, right? Okay. We're just happening to flip it up and down this time. More often than not, we end up flipping it out. You've gotten programmed a little bit to expect it now, haven't you? Yeah. And that's because our original structures are very rarely where the this one is going in the plane. Did that make sense? We can do models. Yeah, model will make this make more sense actually. Okay. Let's go ahead and go to the next chapter. Okay. So this is that next part where we're kind of putting everything together and we're starting to really look at like synthesis, okay? So at this point, I have given you a huge tool belt to use, right? It's kind of broken into pieces, so you don't have an idea of like how do you make a house, right? And these are what these last two chapters are doing. We're kind of like, how do I make actual structures out of this? How do I actually accomplish something with this, with these tools that I've been given now? Okay. So my tools are things like the SN2 reactions, right? The SN1 reactions, E1 reactions, E2 reactions, the additions, proton transfers. Okay. And so, for example, you can do things like you can produce natural products. Oftentimes, when you find a natural product that actually works for something, this is really offensive in terms of like the natural products that they've been finding to cure things like cancer. People are always like, this X natural product can be used to cure YZ whatever cancer. And they're like, why is this being blocked? And they always blame it on the pharmaceutical companies. But the reality is, most of these products are pretty large structures. And then you look at them and you're like, I would have to harvest 1,000,000 of these flowers. They only grow in one climate, one place in the world. I could cure maybe 10 people and I'd wipe out the entire population. Okay? And so this is like a really big problem, actually. The other part of that is like the like black mold stuff. Like fungi, especially, are very offensive for this, where they're very difficult to control. And so they end up doing other things that you do not want them to do, and they end up harming people when you're trying to cure them. So, for example, like Taxol, can be used in cancer chemotherapy. It's first isolated from the bark of a specific yew tree. It is a natural product. We can also get menthol, eugenol. These can be found in peppermint oil and clove oil, respectively. And like, how do you take this? Yeah, you can harvest it from a Pacific yew tree, but how much bark, how much tree do you need to actually get a single dose? There's points at which it just doesn't make sense, right? Are you going to grow 10, 20-year-old to grow trees, harvest the entire tree for a tenth of a dose of it? Probably not, right? The land usage of that makes no sense. So what you end up doing is you have to figure out a synthetic pathway for this. Now, the sort of structures I'm trying to get you to think about is I don't want you to think about I have to put every single functional group on this. What I want you to start thinking about is I see this portion that looks like something else I know. Okay? I see this portion that looks like something else I know. And how can I join things and say an ether bond, right? How can I join things using these different types of mechanisms that I've been looking at before? And so, for example, a really common way is to use an elimination and then an addition to that elimination, right? And so we can put a site that we will then add something to. Okay? And so it's kind of this strategic, when people always say to me, like, chemistry doesn't have any artistic, I don't like chemistry because it has no imagination in it. It's just not true, is it? It's a different type of imagination, right? And it's very strategic. Okay, so these right here are some different starting compound classes, and these are typical reagents or conditions for those reactions that would involve them. And this would be the compound class formed. And notice it's the same sort of reactions that you've been learning for this entire class, right? And so this would be the key electron-rich species that you would use in these reactions. That's the key electron-poor species right there. And these would typically be the reaction type, okay? That's the sections, in case you forgot them. You can go back into those sections, and that's where you'd see those again. Okay. So, for example, if we want to start with an alkyne, right? How can we get a alkyne where we have the R group here, our carbon? So how could we do that? So one of the reaction conditions we can use is we can use a hydride. followed with some alkane with some sort of leaving group, right? Something like chlorine, bromine, iodine, good leaving group. Okay. And so our good leaving group here is going to allow us to very easily follow up an attack, right? Okay. And so if you remember your alkynes, right, this hydrogen, that's an acidic hydrogen. So you can use a base to take away that hydrogen, can't you? You can get a negative charge right there, and then you can attack that carbon there. And that's going to give you that addition of that alkyl group, right? And pretty much whatever you want on it. There's a few limiting rules that we had discussed in these sections, right? But you have a wide variety of things you can add to that. Okay? And so very useful tool. That's like your screwdriver, flathead. Okay. Okay. That's how you use these sort of tables. There's also websites where they've like baked these things in, where you can click on what type of group you have, what type of group you want, and then it brings this information up. Okay. Chem Webbook is probably the best one I've seen, in case you're wondering. Okay, so this right here is an alkylation of a terminal alkyne. Again, we're going to take that hydride, right? We're going to take off the hydrogen right here, react it, make H2. It's a very, very driven reaction, by the way, because you're making H2 gas, which will escape. Okay, so this goes forward to almost completion every time. Very unusual to see it not get incredibly good yields. That's just a proton transfer step that we do. And then that's going to give us the negative charge on this alkyne. Once we have the negative charge, we're going to attack whatever alkyl group we want to add. In this case, we're just going to do a methyl. And we have the leaving group as an iodine right here. Okay? And so the iodine is going to leave. This is an SN2 mechanism because we make a very, very good nucleophile, right? And so we're going to get our alkyl attached now. We have iodide that leaves, and we have H2 gas that left before. Okay? And so this is a pretty good yield reaction. It should be quite successful. This right here is going to be an alkyl halide to a nitrile. And so what we have here is we have the alkyl halide. That's this one right here. Alkyl halide. And then this is going to be using a cyanide agent. Sodium cyanide in this case. And then this is going to give us a nitrile. And again, it's just going to be that same SN2 style attack, isn't it? And so we'll get the cyanide here, Cn-, attacking the carbon. The bromide's going to leave, and we're left with our nitrile product. And so now we've added a nitrile functional group. Notice that I want you to start thinking like it's chess, okay? Or at the very least, start thinking like it's checkers. The force jump rule ones, okay? None of that pansy, not the force jump rules. Okay. We gotta do the strategically, right? And so, like, this cyanide gives us a triple bond position with a nitrogen on, doesn't it? All those cyanide reactions we've talked about before, those have all been unlocked. Okay? Once you get this functional group on. All right, so let's talk about some of these important aspects. Structural features that surround the new carbon-carbon bond in the product provide clues as to what reactions can be used to make that bond. The reactants, which are going to be precursors that would be necessary to carry out that reaction, need to be carefully inspected for the identities and locations of the functional groups. So one of the things you have to be very careful about, would this work well if I had another bromide over here? Would I just get my product? No, I'd be in trouble one time. Yeah. What if I ended up having like this one over here? If I had another group that was even more acidic, would I get my product properly? No, I'm gonna have a lot of troubles with that, aren't I? So you got to be careful that you got to look at the whole structure and go, what functional groups are affected by this? Okay, and that's going to dictate what mechanisms you can use, right? So if I was trying to join two things together and it's a piece of glass, do I want to use a hammer and nail? No, that's a bad idea, right? Glass, I probably want to use super glue, don't I? Okay. And so it's the same concept here. I gotta remember, what am I actually working on? Okay. Is everybody comfortable with the precursor terminology? Remember that whenever we're talking about synthetic chemistry, we're always going to be aiming towards something, right? A target. Okay. And the things that build up to that are going to be our precursors. So let's go ahead and approach this synthesis here of this carbon-carbon bonding forming reaction. So if we have an alkyne here, that's this target here, what could we make from our precursors? Okay, what could we make from it? And so this right here is called a transform. It's how you do this in retrosynthesis. Typically, when you're working in a synthesis, you're going to be working from a target that you want to make, right? You're going to work from something that you want to end up at. Okay? Some final products, yes. And so you'll have like Taxol. I want to make Taxol. Your exact reactants don't really matter that much. It needs to be something you can get your hands on, right? But there's a lot of things you can get your hands on, aren't there? So, like, your options there are not that limited. Okay? Your limiting thing is your final product, isn't it? That's your most limiting thing. And so we're going to work typically in what's called a retrosynthetic analysis, where we work backwards. See this hollow arrow right there? That tells you this is a retrosynthesis. We're actually going to be working backwards. And so what we'll do here is we're going to work from the product that we want to the reactants. What reactants could make this? Okay. Okay. And this is called a transform. It's not called a reaction, in case you wonder. It's called a transform when you see that hollow arrow. Okay. All right. So again, this is going to be a proposed undoing of a single reaction or a set of reactions. It's going to have that open arrow. This is called a retrosynthetic arrow. It's the convention that indicates a transform. It's drawn from our target to our precursor, the thing that we would start with versus what we actually begin. Okay. And again, remember, this is that target that you want to end up at. Okay. 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 Now we have a target here. Again, this is going to be that transform, right? This can be made from. And these will be our precursors right here. Now again, that CC bond here in that target, this can be made from the alkyl halide and that cyanide group, right? Okay. And so this is going to be that transform. That's what we're going to actually end up making. Okay. Is everybody okay with that? Are you seeing that in that reverse order now? Okay. So let's go ahead and approach retrosynthetic pathway here. Right. So in this reaction here, we want to undo an alkylation. So this going the other way would have been an alkylation, right? We add an alkyl. So when we're doing the transform of it, we're going to undo that. We're going to undo the alkylation. So how can we undo the alkylation? Well, there's a few different ways we could try to do this. We could do it there, or we can undo the alkylation here. Okay? Both of those are actually theoretically possible. So what we can do is we can actually use the same reaction we talked about before, where it would have been this undo alkylation. Notice that we don't have to specify all the reaction, like the solvent. We don't have to specify that. We don't have to specify the exact species we're going to use for these reactions. We just have to specify, like, we don't have to say, hey, we're going to use a hydride here. Okay? We just have to, at this point, we're in the planning steps, specify that we're going to undo that alkylation. We're going to use one of those tools that will do it. Okay? And so we're going to have the halide here, and then we would have the hydrogen on this side. And so if you use the hydride here, this would take that off, right? Leave us the negative charge here. And then it should attack that and give us this product, right? And so this is the other way we could have done that alkylation. Let's go ahead and look at another example. And so right here, we have this reactant. We want to get to this product. And so we're going to look at this as a retrosynthetic pathway here. And so what we're going to do here is we're going to have our final product. We want to break this bond here so we can do an undo Williamson ether synthesis. And that would give us these, which would be our precursors, the things we would have to add in. And so again, this would be some sort of leaving group here, and that's an oxide, isn't it? We get that time. Okay, so let's look at the steps for those retrosynthetic analyses. You're going to examine the target for a feature that can be made from a known reaction, something you know. Your tool set here is going to be as limited as the reactions you know. Okay? You kind of have the basic mechanisms and sets of reactions within those that will help you work as your tools here. You're going to apply the transform that undoes the reaction that you have in mind in order to determine the precursors for that reaction. You're going to examine each precursor for a feature that can be made from a known reaction. For each precursor, you're going to apply a transform that undoes the reaction you have in mind. And then you're going to continue applying transforms until you arrive at the starting materials. Okay. Sometimes your starting materials are specified. You have to do something with these materials you have. Okay. Sometimes you have constraints that they will need to be within. They can be anything that's 5 carbons or less. Okay. It could be this list of materials that I would have. Okay. Again, it can be a lot of different ways that you can look at these. This is where creativity actually comes in. There's some artistry here. Okay. All right. So how can we synthesize 1-methoxy-pent-2-ine from the precursors containing 3 or fewer carbon atoms? So this is the product we want. We want some number of steps. That's not super specified here. Less is better, but working is working. And we want 3 or fewer carbon atoms in whatever our precursors are for this. Okay. So think about the reactions that we've learned that can form new carbon-carbon bonds. Is there a reaction that we could use to do this with 3 carbon or fewer atoms? Look for places where you can make those connections, functional groups that leap out and say, hey, I'm something that I could make from a reaction I know. Okay? Those products that you made before. Do you see those products in this? Okay. All right, so does anything leap out and sort of say, hey, I could be used? Anything at all? You could take off the oxygen. That would be one possibility. It doesn't get you as close to your final answer as you might want, right? Because you can only do it on one of these sides, and that really only helps you with 1 carbon, doesn't it? But that would be, you could do that as a retrosynthetic step. There's a bit of a more elegant answer that will kind of solve this problem in kind of one step. You want 3 or fewer carbon atoms, right? So you kind of look here. The 2 options we've talked about is the oxygen right here, making an ether, right? And then we had one where we had an alkyne being added to things, right? And so those were our 2 options we've looked at so far today. 1, 2, 3 carbons right there, right? And this one has 1, 2, and then this would be our 3rd carbon, wouldn't it? Okay. So we're probably going to have to use some sort of combination, because we don't have anything 1, 2, 3 here, and then that'll be 4 for the triple bond. 1, 2, 3, and then we have another one here. Okay, so we're probably going to have to use a combination of the 2 things we had talked about. So, for example, we could split right here. this is one of those options. So if we do an undo alkylation and we split right here, we would have 2 carbons here, and that would be our bromoethane, right? And then we'd have 4 carbons here, and that would be that 3-methoxy-prop-1-ine. Though you don't need to name every single precursor, unless you're going to have to look. Okay? So that gets us pretty close. It's not super far, but yeah, you're right. We're probably going to have to do another thing, aren't we? Yeah. And so again, this right here is acceptable. We're good to go there. But we need to do something else for this, don't we? And that would be that oxygen. We can add that oxygen to our structure. So we can undo a Williamson ether synthesis as our next step. That would give us, well, we need 3 or less carbons, right? 1, 2, 3. So we have to join right there. And so that would be bromide on this side. And then we have an oxide here to attack it with. Okay. And so our oxide will then attack and give us that. Okay, altogether, that retrosynthetic pathway is going to give us this complete synthesis right here. So this is the synthesis written in a forward direction. So this right here is going to be that the undo Williamson ether synthesis that we had talked about. This is that Williamson ether synthesis right there. And right there is our oxide, the bromide there. That's going to give us this product. That product can then be treated with hydride, right? So we get the negative charge there. That attacks this alkyl group right there. And that gives us our final product. Okay. So again, each of the previous transforms could have been undone in different ways. This is, again, you have freedom. There are many options in this, okay? This is an art. You are literally making art in the form of molecules, right? And some of these structures are beautiful and interesting and complex, okay? And so you can make truly fantastic, wonderful things that can save many lives or kill many people, but either way, hopefully saving lives. That'd be nice. But you can do this in almost any way your imagination can take you, right? You do have some constraints, but so does real art, right? And so we have the undo alkylation. Instead of this side, we could have done this side, right? That would have been but1-ine right here that we would have gotten. We could then do an undo alkylation again, couldn't we? To cut up this side. Yeah. And that would have given us under 3 carbon products, wouldn't it? Okay. And the reason you might want to do this is, yeah, 3 carbon, 4 carbon, 5 carbon products are usually things that you could buy on the market. But you might say, hey, what is the cheapest one I can make? Okay. In which case you'd look at these and go, oh, this is ethine. This is really cheap. I can get tanks full of this for like $30. Okay. And so that might be a consideration. The other consideration is it could just give you better yields. And so you have a poor yield one way, you have better yields the other. Okay. And that would be our final synthetic pathway right there. I want you to do it. Show me. Again, there are multiple options for many of these problems, okay? What sort of transform can I do? go ahead and go forward. So what we're noticing is that we have this carbon-carbon bond right here. That's probably the easiest one to deal with, right? The rest of the structure basically looks like we want it, doesn't it? Yeah, we don't have any changes we need to make, so that's the one that should stand out there. And so what we can do here, we can call it an undo an SN2 reaction here. Okay. There isn't a really easy like one step that we could do for this one, unfortunately. If you were to put in a cyanide with the alcohol, it would just proton transfer. Yeah. And so, dang. But we can use that same SN2 reaction we have been using before with the cyanide here. We can use a bromide here as our leaving group. And then all we need to do is we need to do a transform that would take us from the alcohol to the bromide, right? And so like a PBr3 bromination, that would work really well here. Okay. Again, there are multiple options. If you chose another option that would accomplish a bromide switching with an alcohol, like an HBr could work here, maybe not as high yields, but it could work. There are actually a few options you have. Okay. Again, these synthetic pathways are open-ended freeform things. Okay. They are somewhat art. They're science art. This would be your entire synthetic pathway right here. And so you would do this PBr3 bromination. That would give you the leaving group bromide here. This would then be a cyanide attack on that and giving you the cyanide there. And you'd get a pretty good yield from that. So let's go ahead and talk a little bit more about the carbon nucleophiles and the opening epoxides. And so we have here some reactions that can help us form carbon-carbon bonds that are going to center around oxirane or epoxides. An interesting side note to this is actually super common in industry and medical. So like you've probably heard of like epoxy resins or resins in general. The majority of them are epoxies, and the epoxy being epoxide, right? And so this is a fairly high energy group. That's a real nice target. Okay, and so this is one example of that. That would form an OC bond, right? We would form an OR, a nice ether linkage there from this oxirane right here. The other way we could do this, we can attack with a cyanide, and that's going to give us a nice nitrile group there, forming a new CC bond. Very predictable too, because the oxiranes are extremely predictable ring openings. This is the mechanism for that, of a epoxide being attacked for a CC triple bond. And so the first thing we do again is we set up our extremely good nucleophile here by using a hydride. So that same hydride proton transfer gives us our negative charge on our alkyne. This alkyne here, this is a really, really popular first step, by the way, for these things, because it generates hydrogen gas that goes away. So you get incredible yields of this. Very dependable. This is then going to attack the epoxy here. So it's going to attack the epoxide. And this is just going to be an SN2 mechanism where this leaving group here leaves, but it stays attached to the other side. This is going to give us our new carbon-carbon bond. You'll need an acid workup to finish this up, because otherwise you'd have this oxide ending products, which is very high energy, right? And so you do the acid at the end to neutralize all of your base and finish the reaction, so you don't get side products. Okay? And that gives you your final products. And so that would be a nice synthetic pathway for creating this product right here. So this again is the acid workup step here. That's the HCl. You should dilute HCl in water. You can use other types of acids, though be careful that they may react with things. HCl is a very common acid and very nicely compatible as long as it's dilute HCl. Concentrated HCl gets quite reactive, by the way, so be careful about that. Okay, this again is going to be a organometallic compound reacting with an oxygen. And so when we see this organometallic, it can be abstracted as being, yep, the negative charge on that carbon, right? And so it's going to have that negative charge on that carbon attacking that carbon there, right? That's going to give us our product. Okay, so let's look at the mechanism for an opening of epoxide using a Grignard reagent. And so again, Grignard reagent, again, when we see those, they can be abstracted as just being that negative charge carbanion, right? And so we have the negative charge there. It's going to attack that epoxide here. That's going to cause the ring opening. And then we do the acid workup for that proton transfer. And that'll give us our final product here. Okay. And so you'll notice that, again, we have a lot of different sources of those carbons with a negative charge on them that we can use. This is a summary of those retrosynthetic transforms of the reactions I just talked about. Okay, that's the cyanide one, right? That's the alkyne one being generated with hydride usually. And then these are the sort of Grignards that we just talked about, and that's the lithium one right there, right? And again, you can just represent these Grignards, these metallo-organic compounds, as just having that negative charge there, like we talked about way back at the mid-semester. Okay, so how do you synthesize the molecule below, beginning with compounds that contain 4 or fewer carbons? Okay, I'm going to go ahead and start moving forward again. Excuse me. Okay, and so what we need to look at here is what target has a bonding arrangement that would have a 3 carbon plus the OH or a 4 carbon. And so if we look at this, start looking at this more, how many sort of bonding arrangements are there for this? And so you kind of have 2 different ways you can go about this. You could go this direction, or we can go this direction, right? So if we do the first bonding arrangement, we can do this as our transform, which would be a methyl. Yeah, it doesn't accomplish as much, but yeah, it's doable. We could also go this direction, right? So if we go this direction, we can apply this transform here. Okay, and so that's 1, 2, 3, 4. 4 carbons or less, right? Okay. And this one's 1, 2, 3 then. So that one would work. Does this one work okay? 1, 2, 3, 4, 5, 6. By itself, this one doesn't work, does it? Yeah. This would mean that we'd have to add more steps to that. So this is not an ideal bonding arrangement to go with. This one is a much better. Okay, so this is just that onto epoxide ring opening. You could use an organometallic here. That'd probably be your easiest way to go with like a lithium or a Grignard. Does anybody have any questions on that so far? Okay. So this would, for example, be the Grignard reaction. So we've rewritten the transform as the forward-facing reaction. And that would be our reactant here with the majority of our carbons on it. This would be our Grignard. And then for this, because we're going to have that ring opening of the epoxide, we have to do an acid workup to finish it off. And that would give us that product right there. Okay, so let's talk about a few more of these alkylations of these alpha carbons, some regioselectivity and kinetics versus thermodynamic control. So right here we have this carbonyl, right? And we have this iodide right here. You would think that maybe you could do something with like the leaving group and attacking or some suchness, but this would give no reaction right here. And if you use an aldehyde or a ketone and it's treated with an alkyl halide alone, nothing else, you're not going to get any reaction. This isn't a good enough leaving group. This isn't a good enough attacking group, right? So you just don't get reactions here, okay? But what happens if we start treating these with something else? What happens if we start adding a hydride to these or a sodium amide to these? We can start having these alkylations happen at the alpha carbon instead, the next one over. And so, for example, if we use a hydride, we can take that hydrogen off of here, right? Leaving us with that charge right here. And then we can attack our follow-up group, the alkyl halide. Same thing can happen here. So again, we can remove that hydrogen off of here like we'd set up for an elimination reaction, right? And then we can attack using that onto here. Okay. Let's go ahead and look at that mechanism real quick. So again, we have that very strong base, right? And that next hydrogen over from this carbonyl is going to be that acidic alpha hydrogen. Okay? And so what's going to happen here is we're going to have the base give its electrons to that alpha hydrogen. That's going to leave its electrons on the carbon. And that's going to give us the negative charge here. Now remember, because we have that oxygen here, that carbonyl, right? A double bond next to it. This is going to create our enolate anion. It's going to be a resonance stabilized anion. Okay? So we're going to have negative charge on that carbon and on the oxygen in that resonance structure. Okay, so now we have a pretty good nucleophile in that, don't we? So that can act as our nucleophile now. And so we're going to attack with that nucleophile onto the carbon here that's on that leaving group bromide. And that's just an SN2 reaction at that step. And that's going to give us our product. So the alkylation on an alpha carbon is going to be straightforward if there's only one distinct type of carbon to consider. For example, right here we have the aldehyde, right? And so there's only that one spot and that one carbon we have to deal with. Okay. This right here, the alpha carbons are indistinguishable. So ultimately, we only have one we have to actually consider. Okay. But what if we have two completely different ones? Well, then things become important in terms of these non-equivalent alpha carbons. They're going to have regioselectivity. And so the alkylation of your left will give you this product. The alkylation on the right side would give you this one. Okay? And what's going to determine which one's your major product is that regioselectivity we had been talking about in previous chapters for these reactions. In this one right here, if we're looking at this regioselectivity, what we would see is we would have a slightly larger amount of this product on this free carbon that doesn't have anything else on it. We'd still get the other form, about 41% in this case, but we'd get 52% of this one. Okay. And so that regioselectivity is going to control. We can control it partially by choosing different bases. Remember when we were talking about bulkier bases, we can control the which one we would attack. So this is a bulkier base, which is why we're favoring this one here. That's the non-substituted carbon, because the bulky base can fit in easier, right? Over here, we don't favor this one because, again, this would be more crowded. The bulky base is going to have more difficulty getting in there. Now, lithium diisopropylamide, LDA, at low temperatures can cause alkylation to occur at the less substituted alpha carbon of a ketone. The alkoxide bases are going to cause alkylation to occur at the more substituted alpha carbon of the ketone. So we can actually use these different bases to selectively change our major product here. This is actually the mechanism here. So this is the LDA right here. And it's a bulkier base, and so it's going to attack the less substituted side and take that hydrogen from the less substituted side. That will give us the negative charge on the less substituted side, which is then going to attack in that SN2 reaction. And so we'll get the substitution on the less substituted side for LDA. Okay, let's look at this one. So this is going to be the more substituted one. This is going to be the alkyl oxide here. And so it has a bit more space that it can use. So yeah, it's not all these groups right on the base here. Okay. And so we can get more attack on this point right here, which is the more substituted side. This will give us that charge on the more substituted side then, in which case we end up with substitution on the more substituted side. Okay, so that's the difference between these right here. This is actually going to be the deprotonation being irreversible. And that's because this is a very, very high energy base right here. And so if we have an irreversible reaction, then this is going to be kinetically controlled, right? And so what we get here is whichever state is the easiest to access, the quickest to attack, that's going to be the kinetically controlled product, which is going to be this less substituted side. And so that gives us the less substituted side. This is what the energy diagram looks like, by the way. This is why this is considered irreversible, is because it has a very large barrier going backwards, right? Which is what makes that irreversible. Okay, what if this is reversible, though? What you end up getting is just the more stable substitution, don't you? Because it can go back and forth over and over. Okay? And so what you end up seeing is here we have something that the stability is going to be very, very similar to this intermediate state right here, don't you? Okay? You have basically alkyl oxide groups on both of them, don't you? So the energies are pretty similar. And so this ends up being a reversible reaction. You don't have a product heavily favored here. And what you get is a thermodynamically controlled product. Whatever's the most stable ends up being the more likely. Okay? And you don't get a huge difference in terms of the speed. Now, notice that even with all of these factors included, our more substituted side was not that favored. It was still only a 41%. So while we did get significant amounts of product for this, we did not get a huge amount. Okay. These can be somewhat mild concerns, and you can change things a little bit with solvent selection and stuff. So you can actually modify these further. But again, if we are irreversible, then it's kinetically controlled product, right? Whatever is kinetically favored is the one that is going to be the majority product, major product. If you allow these to be irreversible, then you end up with the thermodynamically controlled product. Okay, so these right here are going to be the reversible reactions, and this is going to end up giving you thermodynamic control. So for the products that are competing reactions to be in equilibrium, there must be a way for these products to be interconverted back and forth between each other. And this can happen whenever we have reversible reactions. Even if you have multiple reactions, as long as they're all reversible, you can end up getting the thermodynamic product. And so this is going to take place where you readily have the forward and reverse directions that are going to be similar in energy. Again, this would be what that would look like. So you have reactants. It can make products. These products have a reversible reaction to make either product. And so you'd ultimately get the thermodynamic control, right? Notice that you can actually abstract this to say, yeah, this is just an equilibrium between the two products, isn't it? Because it's going to keep going back and forth as much as it wants. And so you can actually state it like this. And you can actually form an equilibrium with these. And you remember the math you did back in general chemistry with equilibriums? You can actually do those just with two equilibriums that are not directly joined. Okay, kinetic control. This is going to have an irreversible reaction. Okay, so if the competing reactions are going to be irreversible, they do not take place readily in the reverse direction, being irreversible, then you can't establish an equilibrium, and so the products are going to be whatever you formed first. Okay, because it can't go back based on the activation energy. Whatever has the lowest barrier, that's going to be the faster one. So this is going to, again, be these irreversible reaction arrows. You aren't going to form an equilibrium, and so whatever you form first, that's going to build up and be your major product, okay? Because it can't go back. And so reversible reactions tend to take place under thermodynamic control. Irreversible reactions tend to take place under kinetic control. And right here, we actually have an example of this. And so this has less steric hindrance right here. And so it's going to be faster. It has easier access to it, lower activation energy, lower barrier, faster. And so this is going to be the kinetic enolate anion right here. This one's just faster to make. This one right here would actually be the thermodynamic one because this would give you the more stable enolate. And so if you can exchange back and forth, you're going to build up population of this. And so this being more stable, because remember, more substitute is more stable for a double bond. If you're thermodynamic control, you're reversible, then this is actually the one that's favored. Okay. So let's use that alpha alkylations in a synthesis. Right here would be the transform, which is undue alpha alkylation. Again, this would be our alpha carbon here, right? And so an alkyl group that could form from this would be, for example, this one right here, right? And so that would be the undue. You'd have a hydrogen in its place because you have to take that hydrogen off. And you'd have right there your RX without leaving her. Okay. And so these would be the sort of reactions you would see with this, depending on whether you're trying to get the which one you're trying to get more stable. Is it more substituted one, less substituted one? Will change the reaction conditions. But these are both undue alkylations. And if you have ones that it doesn't matter which side you do, whatever you want, whatever's cheaper. Okay. Okay. Let's talk about synthetic traps. Right? Everybody knows that if you design something, sometimes you trap yourself into a bad prospect, don't you? Okay. And so, for example, this right here is an undue epoxide ring opening. Right here, we see this is the less sterically hindered carbon. And this is going to be attacked under basic conditions. If we use the strong acid here, then what would happen to our Grignard reagent? Yeah, we can't do that reaction, right? And so this is one of those fairly common traps that you can get yourself into, is being under acidic conditions and then trying to use something that's a strong base. Very, very common mistake, or vice versa. Being under basic conditions, then trying to use something that's a strong acid. Okay. you're not going to get any reaction. You're going to get a proton transfer, right? And then you'll have no Grignard reagent, and those are quite expensive. So you would have just wasted all. Okay? So pretty common trap, pretty big trap. Don't forget to check these things. Very likely to occur when you have 2 or more functional groups on a precursor that can react in a particular synthetic step. So for example, like on-do alkylation, this is that one we had looked at before. We'd already talked about and pointed it out. But so for this on-do alkylation, you might think you'd do this, right? But what happens if we actually were to try to do that? Well, this right here is also a strong base, isn't it? This right here is a very weak acid, but it's an acid, isn't it? And so would you get the SN2? No. All of this species here, which is probably quite expensive because you're using hydride to make it, would just react with the alcohol and you get the alkoxide right here. Yeah. Now, the funny thing is you very likely could get like a ring closure here and get a totally different product. And so you'd end up with this organic product and you'd be like, what is this? And you could have to work this up for a week trying to figure out what it is. Okay. So it could be even worse than you don't get what you think. Like you may not get a reaction. You may get something totally different. So developing these skills, this is going to just be practice. It is partially art, right? This is just too complex for there to be a super formulaic way of saying, like, you do these steps every time and you get everything. Okay? But overall, by writing them in retrosynthetic pathways, like we've been talking about, where we consider the products in an on-do, you at least will narrow those problems down so that you can then modify conditions and more easily find traps. So some of the problems that you can do to create problems to test yourself on this. Not that you typically need to test yourself on these things, because I think I give plenty of homework. Everybody agree with that one? Yeah? Okay. Fair enough. You can start with a structure that has a relatively small number of carbon atoms and contains functional group that you know can participate in reaction we've studied. And so you can do like the different reactions you've studied and start yourself out with those functional groups. You can carry out reactions in a forward direction, keeping track of reagents and conditions, and determine the products. Make sure when you do these things, though, pay attention to your stereochemistry and regiochemistry, because that's a large part of what's actually useful doing this. Repeat until you have created a product that has a result of 2 or 3 sequential reactions, because this is the sort of typical synthetic that you do for like a easy undergraduate synthesis. Okay, a graduate level synthesis, you're talking more like 20 steps. Okay, treat the final product as the target and ask how the target can be made from the starting structure. Now, this is actually something that if you go to graduate school and you're a synthetic chemist, like your group, they'll do this. They'll like design problems and then they'll turn around and give you the target. And like you'll swap them between each other in like a rotating structure. And then have to come up with synthetic pathways, and it's kind of like a bragging right thing. It turns into a game where I stumped you. Yeah, and you'd make fun of them a little bit. Yeah. So this is some example like designing your own problems you could do. So you can like do an ether here. You gotta go into an alcohol. So the overall synthesis we just did, but we could phrase that as a problem instead. So don't try to work it. You already know this solution. You can work this with partners where you can like swap problems and go, I think if this could happen, you think that. Okay. See if your proposed synthesis has synthetic traps, and then how do you overcome those synthetic traps? Can you do something to remove the synthetic traps, or can you use a different mechanism? So suppose your study partner constructed the following synthesis problem, gave it to you to solve, design a synthesis that could be used to carry out this transformation right here. So how could you do this transform? I'm going to leave you on this, and this will be our clicker for next time, okay? Okay. Try it out. I am. I am. Did you want the 1 minute? Okay. That's fair. No, it's just good. It's such a good stopping point, right? Yeah. Yeah. I couldn't think of a better stopping point than. It'll be due Friday or Thursday night, the end of day Thursday. So it doesn't really have the last review. Oh, okay. My fourth review, I've changed that. Yeah. Yeah. On the SmartWorks. Okay. Yeah, I changed that yesterday sometime. Oh, did you? Oh, sorry. So you had to do this. Is it still showing your score okay? Let me know if I messed up your score.
I was wondering to review what I got wrong, the naming portion, and fix the last exam.
Oh, okay. Yeah. Yeah, remind me.
Okay.
And whenever I get a chance today, I'll release the sheets and all that.
Okay.
Yeah. I think everybody's taking it, so I think I'm
So,
good. Yeah.
She's really sad about it.
just trying to. I'm gonna come back to for that isolation of coffee lunch. Should I meet over here before we usually do that?
I don't remember if we have a class in there. Meet me in my office and we'll check.
And I
Okay.
have to go to my natural thing.
Yeah, I think we can put you on an open desk, maybe.
That's what I was.
Okay.
If I want to get
So
chapter
I
12
don't know
in
if
one
I-
ECS, I mean the
I like
MCAT
this yarn.
reviews, can I get it done during next week? Like
Yes.
even if after,
I'm gonna send you all
The
the color
exam.
options that I want.
Yeah, but it's minus 1% per day.
well, I don't remember the due date for chapter 12, but the MCAT doesn't have a due date.
Oh, yeah, the due dates, the MCAT's shut, yeah.
Yeah.
Yeah, the chapter 12 has a due date. I don't remember what I put it, actually.
I checked
Yeah.
it, but I forgot.
Yeah, that would make sense. Yeah, I probably didn't touch it. I could actually move it back if you
Can
remind me.
move it next week?
Yeah, remind me because
'Cause I
I'm
wanna get
gonna
it
be.
done for-
Yeah, send me an email to remind me.
I want to get one of the MCAT chapter 12 done, but I think this week is pretty